afternoon, everybody. So my name is Marc Brasher. Happy to be here to present Master Cyber Operator's perspective on AI for OCO, or what I wish I knew when I was conducting operations. Bottom line up front, I'm not a PhD math guy, I'm not AI, I'm not from academia. I'm a cyber guy that just got told to go learn AI and help shape. I got a strong cyber background. I can talk cyber nuance and talk to the PhD math, mathematicians and AI folks, and really work together and collaborate and come up with really innovative stuff. First, wanted to thank MCPA for having me. It's been really great to give back to the community. So about me, I served 14 years active duty in the Air Force. I'm now in the Air Force Reserve in the first ever OCO unit for the reserves. I'm a senior master sergeant there, helping shape what it means to do OCO for reserve airmen. Went through Riot in 2013, certified as a CNO journeyman operator. And just last fall, I was certified as a U.S. Cyber Command Master Cyber Operator. And again, a lot of upskilling, leaning on my team. I'm still a cyber guy. I just happen to know a couple AI terms and techniques and kind of know how to put stuff together. So today, we'll begin with a very brief intro to AI and hopefully level set on some of those terms and techniques. I'll cover how industry and our adversaries are adopting AI, in addition to general use cases that are perfectly suited for AI, and then move on to some very highly relevant mission-specific examples that would be relevant to everybody in this room. So, what is AI? Machine learning models comprised of algorithms trained on large amounts of data leads to a sort of intelligence exhibited by machines. Noted is intelligence exhibited by machines. It's not that they themselves are intelligence, it's that through a lot of training, it appears as though they have intelligence, right? Artificial intelligence is the overarching umbrella term for the scientific field, of which you have machine learning, deep learning, and generative AI, which is the most recent breakthrough. But all of those are fields underneath the overarching artificial intelligence umbrella. In the 30,000-foot view, so the extremely simplified example of how you would create a model is you would initialize a matrix with random values, normalize your data, feed your data through the model, calculate your error, back propagate the error through the weights, and then continue that loop until the error and the accuracy kind of converge, meaning they're no longer improving. This, of course, simplifies it almost to a fault in that it doesn't include data normalization, data engineering, data normalization, right? That's a whole field in and of itself, and you can't really get to this point until you've massaged your data into something that you can really work with. So here are two really contrived examples where machine learning models work really well. On the left, we have a very linear problem, house prices to square footage. And so we can use a machine learning algorithm, really linear regression, to fit a line. And then you can say, hey, at square footage of 5,000 square feet, what's the average home price going to be? And we can fit that line and change it over time as parameters change. The next step in this type of problem would be to include additional features. So how large is the plot? How many floors are there? What's the mean home cost of properties around it? And then you would start moving into the next plot, which is a non-linear problem. And machine learning models perform really well here. And we can kind of get to a point where we can understand the disparate data points by where they're placed in the plot in conjunction with their labels. So there are two types of learning models for AI. Obviously, we have supervised and unsupervised. In supervised learning, you have labeled training data, like you heard before earlier today, like whether a web request is malicious or not. You then feed that data through the model, and the model learns patterns and relationships between the input data features and the label, right? So you have the data, the features of that data, and then the relationship to the label. In unsupervised learning, however, the data is not labeled. The model takes actions in an environment, and then we train it by creating a reward model where we increment the reward when it takes an action we desire and decrement the reward when it takes an action that we do not want. Like data engineering, reward shaping for reinforcement learning models is a very important process in and of itself. The techniques and the literature for reward shaping largely determines whether or not your model will be successful or not. Large language models, so everyone here has learned about large language models thanks to OpenAI, obviously. Large language models, or LLMs, are trained on huge amounts of data compared to previous model. These are on the orders of petabytes versus gigabytes. It's just astronomical. LLMs are a significant breakthrough for natural language processing made possible by the transformer architecture. And I've linked to the paper here for anybody who wants to read it. It's beyond my scope, I'll say that much. LLMs have created the generative AI field, which is being used for increasingly complex tasks. There is an astonishing amount of academic research, and that is being published each month, and LLMs are continually being improved and adapted to more and more complex workflows. So retrieval augmented generation. This is the hotness on the streets for anybody who's wanting to employ LLMs, a foundational LLM in your environment. So retrieval augmented generation, or RAG, is a very popular technique to use generative AI models to evaluate data that did not appear in its training data set. We perform a similarity search and other kind of prompt engineering techniques against the user's prompt to retrieve context from a vector database, and then we send that as context to the LLM with the prompt. And then the LLM is able to evaluate and give us an answer, even though it wasn't trained on that specific data. So in this example, I built a RAG pipeline on a number of companies' financial disclosure documents. And in the top, I asked it a very specific question about the information in those disclosures. And you can see that ChatGPT is like, I don't know what NVIDIA was doing in 2023. My data stopped at 2021. But if we include RAG and send it to the LLM at the same time, so we send the prompt and the context at the same time, the LLM is able to respond and give you highly relevant, highly specific information, even though that information did not appear in its training. So it's well known that the technology industry has adopted some form of AI for search, advertising, and product recommendations. Here are some other areas that not be as well known, such as Netflix using AI to determine locations for film production. That was like news to me. I didn't realize that at all. So some emphasis here that I have made personally are specific areas that companies are adopting AI and using them for highly complex and maybe even highly risky areas. Fraud detection, market trading, equipment failures, flight automation, air traffic management. Those are all highly complex tasks that are generally performed by subject matter experts, and they're being augmented or automated through the use of AI. Moving on to our adversaries, public reporting for China and Russia's adoption of AI is well known. There's no shortage of news sources reporting about the use of AI in the Russia-Ukraine war. China specifically, with their very overreaching government surveillance and their social program. Also, election influence is a big thing. That link is to a very recent article where China demonstrated that ability. All this to say, future wars are likely going to be decided in part by how we integrate AI into kinetic and non-kinetic warfare. So AI can be adopted to every industry for different purposes. AI models are identifying new treatments for healthcare, improving processes and efficiency, and making predictions, giving underlying patterns in data. Here are some specific cybersecurity applications for AI. AI excels in analyzing huge swaths of data and providing recommendations to analysts, and can nearly conduct full incident response investigations by identifying relevant events to a network breach. Antivirus vendors' adoption of AI is making penetration testing more difficult. It's not impossible, but I suspect in the future, red team engagements and penetration testing is going to be AI pitted against AI. So let's get into some very relevant areas to this crowd. I've conducted somewhere close to 700 ops for the NSA and US Cyber Command. So as I've gone through this exercise over the past year of trying to learn AI as deeply as I can and as quickly as I can so that I can be relevant for my team, I'm always considering and thinking about and reflecting on, hey, when I was doing those ops 5 years ago, like where are the areas where I could have used AI and automated or made it more efficient, or maybe identify something that, just because of exhaustion, something I just missed and it led to a failure, right? So please note that I generated hypothetical data sets, so none of this is like mission related, none of this is classified. I just created data sets and then I fed it to an LLM and I said, do a thing for me. So they're going to be presented in kind of low complexity, then we'll kind of walk up the chain to higher complexity and higher risk. So starting with low complexity, we've got analysis and reporting. I see this as a no-brainer. Answering intelligence requirements is an important task for obvious reasons. By building a pipeline like this, we can prompt a model to evaluate disparate and unstructured data points and determine if our intelligence requirements have been met. So what this might look like is we can take our J2 prioritized intelligence requirements, our essential elements of information, and our commander's intelligence requirements, feed them into a RAG document store, and then we collect some target data through whatever means necessary, and then we can create a workflow where we say, hey, what of this data that I've collected, what of my intelligence requirements have been met? And then we can generate a report, we can send that out as a WAR, we can send it up to leadership, they can make informed decisions, that can shape what ops get done next week. Analysis prioritization, so using multimodal models and performing bulk analysis across substantial amounts of data, we can prioritize analysis for our analysts. By ingesting the prioritized intelligence requirements, we can leverage AI to augment the human element of analysis and streamline review of information to more quickly identify mission-relevant information. So consider our analysts have terabytes of information that they have to manually go through, and they don't really know how to make sense of it. We can plug in an AI model that says, hey, review everything that we have, everything that exists in this database. Analyze it for anything sensitive, identify any relationships with other vendors or maybe the state itself, extract any relevant information that we might need, and then prioritize that on the list. So our analysts can work down the list in prioritized order and review the things that are highly relevant to their mission, and hopefully get better information quicker to drive operations. Trend analysis, so anybody who's been in a technical director or mission director roles knows that trend analysis is a very critical task for operations, and it can determine the long-term success or failure for operations. So for example, if we have a model that can identify tool failures, trends in operator error, or changes to security posture kind of at large for the command, we can analyze that and determine what changes do we need to make now to prepare for what we're seeing in target space, to include changes in tradecraft, changes in training, and everything of the sort. Very similarly, gap analysis, so reviewing operations or individual steps for missions that fail, we can gain insight of these operations over time and identify when capabilities or tradecraft are missing or need further refinement. This is especially useful for generating requirements or informing acquisitions processes. So given 1 month, 90 days, whatever the interval looks like, we analyze all of our engagements. We note when something failed, and whether that was on us, like we did something poorly, or we didn't have the necessary tradecraft in place, We can generate reports, feed them to our technical leadership to say, hey, like we need additional widgets for this thing. And then they can generate requirements and put those out to vendors or internal research. Open source intelligence. So this is a particular area where I think AI can really augment analysis. In most cases, OSINT requires manual analysis of an enormous amount of data. And we can use AI models and LLMs to, again, kind of like what I was speaking to before, distill it, summarize it, prioritize it, so we can quickly gather artifacts from the data and make mission relevant decisions to gain access or identify relevant targets or whatever your use case might be. In this example, I did a subdirectory scan for Leidos, and I said, like, hey, what is the report that I found in my subdirectory brute forcing is relevant? And it highlighted like 6 things that it saw. And then I, as the analyst or the operator, can continue prompting the LLM to identify other things, or we can do a multi-turn conversation. But ideally, we can use this to immediately kind of understand the data without having to manually go through every little bit of it. So moving up the ladder to medium complexity and risk. So we have black box analysis. By incorporating novel prompt engineering techniques, we can use AI models to generate intelligent fuzzing targets against samples to discover bugs. This type of analysis usually requires exceptional experience and subject matter expertise in software development and reverse engineering. But with automation and generative AI, we can streamline engineers' times and lower the skill floor. This process can be further improved with RAG. So this figure that I show here, this is from Google OSS Fuzz. This is an open source-ish fuzzing platform that they have created. You have to sign up and your project has to be so popular before they'll include you. But they're utilizing AI to generate fuzzing targets, and they've identified nearly 30,000 bugs across 316 projects. And that's primarily through AI automating and streamlining that workflow, and then an engineer just goes and validates what it found. Cyber threat intelligence. Collection and analysis of threat intelligence, SIEM logs, IOCs, and APT reports can lead to improved signatures, identifying changes and patterns of actor tradecraft, and automating the testing and deployment of change management processes. In testing, my company has had success in using LLMs to generate Sigma rules from cyber threat intelligence and then deploying those into a SIEM. Any SIEM vendor, Sigma is a SIEM platform agnostic rule set. So we can consume a threat report or threat intel, look at IOCs and say, hey, from this threat report, how do I generate a Splunk SIEM log and deploy it, and then we can do internal testing, make sure it doesn't block anything well known, and then go from there. Subversion. Intrusion detection systems and intrusion prevention systems generally rely on rules or signatures that evaluate traffic to identify malicious activity. Using reinforcement learning, we can seek to train a model to manipulate a request to subvert the known or unknown protection rules while also preserving the logic in the original request. In this example, this is a real subversion we generated using a reinforcement learning model, and the modified request bypassed the web application's firewall rule set. So imagine, any normal IDS or WAF product, we can manipulate attacks to enumerate what the rule set might be, and then mutate it to bypass the rules. I would also urge you to consider the inverse of this. So we can modify requests to bypass the WAF. What if we turned the model around and said, hey, monitor the incoming traffic and see if the requests coming in look like this? So now you've got a reinforcement learning model for both attack and defense. Mission planning. By building RAG document stores of intelligence and tradecraft, we can prompt LLMs to generate mission plans relevant to current capabilities and TTPs. This process can be fine-tuned and adapted by providing commander's intent, intelligence gaps, or even the level of accepted risk that you have for a particular mission. By training a model on years of executed operations, which we know we have that kind of data, right? The model can streamline plan creation and remove the heavy burden on analysts. I'm sorry, the pictures are kind of small. The final category, application areas with high complexity or high risk. So command and control. Building upon the OSINT pipeline I mentioned earlier, we can model what the baseline communications of a target might look like. And then we can then we can infer how well our command and control traffic blends in. And then identifying underlying patterns in that data, we can mimic that traffic beyond open source techniques. So taking traffic that we've collected, we've identified it, we've run it through a model, we've identified patterns in the data that exists. We can use the model to identify those patterns and then create utilities to alter our command and control traffic to blend in with the known good or the baseline. Evasion frameworks, by training a malware classification model and automating evasion technique alterations in build pipelines, we can continually generate and mutate capabilities and payloads to bypass security products or employ signature diversity. These models provide substantial value in attempting to bypass defensive-based AI models. So remember before when I was talking about AI pitted against AI? This is a real framework that we've built and automating through CI/CD pipeline, push and build whatever your release is, and then have it mutate it in real time. And we've had a lot of success in being able to bypass a lot of the well-known EDRs. Vulnerability research and reverse engineering, an area very rich with current public interest and academic research. There are many approaches where we can integrate AI into reverse engineering workflows. LLMs have proven the ability to identify latent patterns in data, which serves particularly well for deobfuscating code. Comparing current samples to a large data set of previous examples, we can collect immediate observations for reverse engineers and streamline that workflow dramatically. In this example, we show that ChatGPT has analyzed obfuscated JavaScript and immediately picked up on what it's doing. And in the next example, further down, I asked it to produce the original sample, and it was able to produce it without any further prompting or context. Network path traversal. Using graph neural networks with knowledge graphs, we can identify kill chains or attack paths in a network to gain access to key cyber terrain. On the left is a hypothetical enterprise network, and after training a graph neural network model, we can prioritize specific attack paths that take into account risk tolerance, network and endpoint security characteristics, and situational awareness. This type of model also has huge value for both offensive and defensive applications. So when I imagine this, as we build this out, when we first gain access, when we first get initial access to something, if you imagine like a real-time strategy game, the fog of war, you can only see kind of what's immediately around you. And as we kind of laterally move and we scan and we get information, the fog of war pushes out and we can see more. And then using a graph neural network, we can say like, hey, we're here, we want to go there. What are all of the available paths for me to get there, knowing what I have in my toolkit? And that gives us the ability to take attack paths given the situational awareness we have in the network. So maybe there's one path that traverses a node that has NetFlow or centralized logging. Maybe we don't want to go that way. Maybe we'll take the long path around, maybe go 8 hops to avoid that central location, but still gain access to the key cyber terrain and still meet commander's intent while protecting the toolkit. And finally, real-time operation analysis. So this is the tool that I'm actively working on, building a RAG document store of cybersecurity-related material. We can prompt an LLM to triage and evaluate individual commands being executed by a red team operator. in real time. And since we're using RAG, the LLM can recommend current day CVEs, identify misconfigurations or offset concerns. And so in this example, I have an operator terminal here that I've integrated with an LLM. And each time I run a command, here I was just running uname tac A, a watchdog sends off the command to an LLM, evaluates it against a cybersecurity related data set that I've created, and then it makes recommendations through some prompt engineering that I've given it, but it's able to recommend, you can see here, a CVE from 2023, even though the model I'm using was released in 2022. So ideally, if this were something that we looked at for use in this kind of arena, you would integrate it with post-process data, something ideally that you can get in real time, but you could build a data set comprised of, say, JCTM or Confluence or Jira or whatever your knowledge management is, and that way the LLM is able to make recommendations based on your tradecraft, your tools and techniques. And the other pipeline for this that I didn't create a demo for is, if you are on the same system a dozen times and it takes you 2 hours to triage to make sure nothing's changed OPSEC-wise, we can use an LLM in this manner, in this same style of manner, and we can say like, hey, here's my survey, here's today's survey, here's the last 10 surveys, tell me what's changed. And it can immediately pick up on, root user logged in at this time, he looked at varlog messages and then he left. Or a user logged on and they deployed a patch, right? And so instead of me needing to wait 2 hours to do a triage, I feed in my survey, it identifies any changes, and then I get to, that's 2 hours that I get back to doing the mission. So that concludes my presentation. Hopefully some of these examples triggered an aha moment. That's kind of what I was going for. Something to really jog your memory. Think about your processes, the things that you're dealing with today, and seeing some of these examples. Hopefully it would make you think of how to take this back into your workplace and either work amongst yourselves to create small widgets that solve a problem, or worst case, submit capability development requirements and send those out to maybe get like a machine learning engineering team to come in and make these types of widgets to support your engagements. Thanks again to the MCPA for having me out. This has been a great opportunity. Are there any questions?
Yeah. For that cert one, like how would I get started? I'm with First IO red team, so I could definitely some of the stuff you talked about. But I'm curious, would you ever really trust an AI to do survey? Because I could just see like an AI do it and Lucy, and it's a logged user, and I got caught and burned because you trusted an AI.
Sure. Yeah, I mean, it's definitely a trust but verify early.
So don't trust.
So I think you can get to a point, right, today with LLMs, I don't know if you're familiar with the temperature slider for LLMs, but you can basically tell it how much varied its answer can be. So you can prompt at the same time and get a different response. So in my testing, I've seen it would pick up on a core dump one time, and the next time I fed it the same command, it would recommend something else, right? And so there are some techniques that you can do where you send it several prompts of the same thing, and then you gather them, and then use an LLM to distill it down. But obviously, it's definitely like a crawl, walk, run. It would be, in my case, and the way that I would implement it if it were up to me, is the operator would still be in full control, and the analyst would be the one picking up on what the LLM is receiving. And then the analyst can be like, hey, did you see this? Did you see that? And so they're still using their tradecraft, they're still doing everything without being interrupted, but the analyst is getting feedback from the LLM, and then they can collaborate between the operator and the analyst.
So if the operator, this is something, it's still on that, right?
So in that example where the operator is, they're operating an abstraction of the LLM, and it's the analyst that's seeing it.
Okay.
The team is still responsible for making sure that they see that stuff, right? But I think there's a world where with enough data, with enough training, there's also fine-tuning techniques like reinforcement learning with human feedback, where if you don't if it's not responding the way that you want, you can provide it context and then kind of prioritize what you want it to see.
Just a quick question. So I guess you're tying into the data database for a lot of the stuff that you're using?
This is all open source, like running off a data set that I built. Yep.